Okay, so now let's go to 4 areas of electron density. We already talked about 2 and 3 in the previous video. Let's do 4. So the next molecule we're going to do is methane CH4. If you crunch the numbers, S is equal to N minus A, you'll get something like that. That's 4 areas of electron density. Anytime you have 4 areas, the electron geometry is called tetrahedral. Tetrahedral. And because you have no lone pairs around the central atom, the molecular geometry would also be tetrahedral. Remember, anytime there are no lone pairs, molecular geometry is the same as electronic geometry. Okay, what would the bond angles be? Well, this is what a methane looks like. This is what a typical tetrahedral looks like, okay? And if you do the bond angles, and basically take a sphere and divide it up this way, you get 109.5. Okay, so those are your bond angles. Okay, what about polarity? Can you see that all the peripheral atoms are exactly the same? And can you see that there are no lone pairs around the central atom to mess things up? So this would be non-polar. If, on the other hand, you changed one of these hydrogens, and let's say you made it into a fluorine, you've messed up the symmetry, right? And so therefore it would be polar. Okay, everything else the same, but it would be polar. Okay, good, that's that one. Let's move on. Again, practice doing all of this. Practice creating the Lewis structure yourself. All right, the next one we're going to do is ammonia, which is NH3. If you crunch the numbers, you'll see that this is the way it's going to look. Okay? How many areas do you have? Also 4. Here's 1, 2, 3, 4. Okay? 4 areas. Electronic geometry is tetrahedral. So remember, 2 areas electronic geometry is linear. 3 areas electronic geometry is trigonoplanar. 4 areas tetrahedral. And hopefully you remember this from intro chemistry days. Okay, what about the molecular geometry? Well, now it's going to change, right? Because you have a lone pair there. So the molecular geometry can't be the same as the electronic geometry. And let's take a look. This is what ammonia looks like, and this is what the methane look like. See how different they are? Their shapes are different. Why are their shapes different? Because this guy's got an actual atom up here. This one doesn't. So this sort of looks like a pyramid with a triangle at the bottom. So we call this shape or molecular geometry trigonal pyramidal. So let's go ahead and write that down. Trigonal pyramidal. Okay, that's the shape. So 4 areas of electron density, always tetrahedral electron geometry, but the molecular geometry or the shape is going to be different because you have this lone pair here, different than this guy. Bond angle is also approximately 109.5, but it's a little less than 109.5. So 109.5, but actually a little less, again, because this lone pair repels these guys more. So I'm going to sort of redraw it to make it sort of look like, let's see here, maybe draw this pointing out, draw this pointing in. I don't know. I'm not an artist, but that's my pretend trigonal pyramidal, or sometimes people will just do this to make it sort of look like a pyramid a little bit. Something like that. Okay? All right. Is it polar or non-polar? This one's definitely polar. Why is it polar? Because we've got that lone pair on the central atom. It's not all symmetrical throughout. You've got 3 hydrogens, but then you got the lone pair. So that messes up the symmetry. It's it's polar. Okay, good. Next one is water. I hope you all know that water is the most polar thing. So obviously expect that to be polar. This is what water looks like. If you crunch the numbers, this is what it's going to look like. Now, you could have first drawn it like this, which is fine, but it's a little deceptive because it makes it look like it's a linear molecule, but it really isn't. It's got 4 areas of electron density, 1, 2, 3, 4. 4 areas means tetrahedral. So the electron geometry is tetrahedral. The molecular geometry, this is what water looks like. Here's the oxygen and the 2 hydrogens. This is what your water molecules look like. It's definitely not linear, right? It looks bent, angular, sort of like that sulfur dioxide looks. So I'm going to write this bent. I'll put /angular. Again, it depends on what OWL wants you to write. It could prefer bent or angular or what, you know. Just know both terms so that you use whatever needs to be used. Okay, what about the bond angle? So it's going to be less than 109.5. Actually, water specifically is 104.5, but bond angle is going to be less than 109.5. Why is it less than 109.5? Because these 2 lone pairs repel each other more than the 2 bonded pairs repel, so it sort of closes it even more. So instead of being 109.5, it just closes it even more. And it's definitely polar. Why is it polar? Because these 2 guys are not opposite each other. Like the way, if you had drawn it like this, it would look like they're opposite each other and they cancel each other out, but they're not. They're on either side this way, so they don't cancel each other out. It is polar. Okay, so we're done with the 4, and we're ready to move on to 5. Now, for those of you who are fresh out of Chem 1050 or Intro Chem class, we usually just stop at 4. But now, because we know that we could use the D zone and we can have exceptions to the octet rule, we'll go ahead and do PF5, Phosphorus Pentafluoride. And it's one of the ones we did in the previous video when we were doing chapter 9. So for this, for the way we're going to do the 5, we have to have 2 of the peripherals in the axial position, meaning up and down, okay? And then the other 3 are in the equatorial position, meaning around the equator, around the middle part. This is a wedge going out, and this is a dotted line going in. And then I'm going to put all the lone pairs, which are a little annoying, but we'll do it anyway. Okay, so phosphorus pentafluoride looks like this. This is what it actually looks like, okay? So think of this as a phosphorus, fluorine, fluorine, and then see how the 3 fluorines are around the equator, all the way around here, okay? So these 2 up and down here are called the axial position. These 3 are in the equatorial position, okay? So 5 areas of electron density, 1, 2, 3, 4, 5. Anytime you have 5 areas of electron density, the electron geometry or electronic geometry is called trigonal bipyramidal. Trigonal bipyramidal. Because it looks like you have 2 pyramids on top of a triangle. So see, the middle one is a triangle, and here's a pyramid and a pyramid. Trigonal bipyramidal, okay? The molecular geometry, can you see that there are no lone pairs around the central atom? Remember how I said, any lone pairs around the central atom, the molecular geometry is going to be different. There are no lone pairs, so it's the same. Trigonal bipyramidal. Okay, what would the bond angles be? All right, this is pretty cool. You can see this over here, this fluorine, phosphorus fluorine. This looks like a perfect 90-degree angle. So one of them is 90 degrees. Okay. Can you see in this equator area, can you see it's like a circle divided into 3 parts? So that's each angle here is going to be 120. So 90, 120. And then can you see the two axial ones from fluorine, phosphorus, fluorine, this long line here, that's going to be 180. So you have three possible angles, three angles in this trigonal bipyramidal. Okay, what about polarity? Can you see that everything is symmetrical? All the peripheral atoms are exactly the same. This fluorine and this fluorine cancel each other out. These three fluorines are perfectly situated in this on the equator. Think of them as three possible vectors, all cancel each other out. So it is non-polar. Okay, if any one of these fluorines was replaced with a chlorine or a bromine or a hydrogen or whatever, then it would be polar. But since they're all identical, it's nonpolar. Okay, good. Let's do one more and then we'll stop this video and then do another one. All right, one more. Let me see which one I have here. Let's see which one. Sorry about that. I should have looked at it before I got started. Okay, SF4. Okay, good. Yep. SF4. So let's go ahead and crunch the numbers for this one. S is equal to N minus A, just to remind you about how to do these things, okay? Remember the needed is 8 for everybody, so that's 40. The available is the valence electrons. Fluorine is 7. 7 times 4 is 28. And then the sulfur is 6. And you've got 34. Okay, 34. So 40 minus 34 is 6. This is telling you that you've got 6 bonds. Obviously, it's not 6 bonds. Sorry, forget I said that. This is telling you that you have 3 bonds. Obviously, you're going to have more than 3 bonds. You're going to have 4 because we've got 4 peripheral atoms. So let's go ahead. We don't know what it's going to look like. We have to change this 6 to an 8. Remember how I told you guys you need to do that, okay? Okay, so we used up 8. 34 minus 8 is 26. So now I have to distribute 26 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Where do I put 25, 26? On the central atom. Okay, now I look at it and say, oh my goodness, I've got 1, 2, 3, 4, 5 areas. Anytime it's 5 areas, the electron arrangement has to be trigonal bipyramidal. So now I need to redraw it so it looks trigonal bipyramidal. In these scenarios, you put the lone pairs in the equatorial position, not the axial position. So let me show you what I mean by that. So remember how I said 2 axials, axial, axial. I'm going to put the lone pair here, and then I've got another fluorine here and one here. Okay, so this is the way it actually looks, not this way. This is what we drew just at the beginning to see how many areas we've got. Okay. So this is what it looks like. All right. Remember, if you have a lone pair in a trigonal bipyramidal, the lone pairs are always going to go in the equatorial position, not the axial position. Okay. So what does it look like? The electron geometry is trigonal bipyramidal, because anything with 5 is always trigonal bipyramidal. But now let's take a look and see, what about the shape? See, it doesn't have this guy anymore. So what's the shape? You know what they call it? Tilt it over like this and think of you sitting on one side and someone else sitting on the other side. This is a seesaw. Don't call it teeter-totter, it's a seesaw. Okay, so the molecular geometry or shape is called seesaw. I don't make this up. This is what it is. The angles, we still have a 90, a 120. Here's the 120 in the equator, and a 180 in the axial. So we still have 90, 120, and 180. And now it's polar because we've got this lone pair. Polar. Okay, good. We have one more or two more of the 5 areas, and then we'll do the 6th area. So we'll do that in the next video.